Better late than never. Anyway, Yegor, does this make any sense? Maybe somewhat or no sense whatsoever.
For me, it's not clear.
Okay, Leonid, let's have a look. So we have a section which is we have a connection which this time we view as a differential operator from sections of S to sections of S times the cotangent bundle. Now suppose I also have a section of the tangent bundle. What do I do? Locally I can represent the section of the tensor product as a sum of the tensor products of sections of the individual bundles. So locally, I have this number of S equal the sum of products of tensor products, and in these tensor products, the first component will be from S, and the second component will be from the cotangent bundle. And now suppose I also have a vector field, and I can take the cotangent component and evaluate it on the vector field. Well, I get a function. And then what remains is the first component, which is a section of S. Значит, Леонид, давайте еще раз посмотрим. Значит, у меня сечение расслоения S тензор Q-касательный. Но Q-касательное можно применять касательно и получать функцию. Точнее, сечение Q-касательного можно применять к сечением касательного и получать функцию.
Да.
Ну, пусть у меня сечение, значит, сечение вида сечение тензорного произведения расслоения, которое имеет вид сечение одного расслоения, тензора сечения другого расслоения. Ну, тогда я просто могу свернуть Q-касательную координату с векторным, то есть Q-касательное вот это вот сечение с векторным полем.
Да.
Но после того, как я сворачиваю, что у меня получается, у меня остается только сечение самого S. Ну, локально
Да.
все, значит, все вот так вот, значит, так вот раскладывается. В общем, это можно немножко более бескоординатно сказать, но в принципе, по-моему, более-менее уже значит, понятно, что происходит.
Ну да, сейчас понятно. Спасибо.
Так, не за что. Так, Владимир, Егор, значит, имеет ли это все хоть какой-нибудь смысл?
Да, пожалуй, что имеет. Ну, более-менее ясно, да.
Simon, does this make any sense?
I'm somehow lost, but I guess if I look at it all over again, I guess it's gonna be clear. But
Well,
I mean, I feel a bit lost.
Let's suppose we have a section of S tensor the cotangent bundle, which is the tensor product of a section of S and the section of the cotangent bundle. And then I can take the cotangent component and evaluate it on the vector field. And what I get is a function times times the section of S. Does this make sense?
Yes, it does. Yes.
Okay. Well, but locally, all sections of the tensor product can be written as sums of the tensor products of something from S and something from the cotangent bond. And then we apply the same procedure to every term in the sum.
Yes, I guess now it's clear. Yes, thank you.
Okay, so let's look at the definition of the Dirac operator. We have we have this nabla EI of S, which is a section of S. And then I Clifford multiply this section by EI, and I get another section of S. Why? Well, because we assume that S is has a structure of a module over the Clifford output. And we basically well, we have an expression on the right which makes sense, where EI with an upper I and EI with a lower I are well defined and orthogonal. Okay, now I will list some basic properties of the Dirac operator, and and then we'll have a break. Well, first of all, the operator is independent of the choice of a local basis, of a local orthogonal basis of the cotangent bond. Property number 2. Okay, I will write this as the symbol of the operator at xi, where xi where x is an x and psi is a cotangent vector, is Clifford multiplication by psi. Where does it go from? It goes from Sx to Sx. I want to show that this map is invertible. Well, I apply it twice. I get Clifford multiplication by the by minus the norm of psi, and this is non-zero for psi different from 0. So D is elliptic. And so is D squared, which is called the theoretical plation. As a square from the formula for the symbol, the symbol, the operator sort of resembles the usual Placian operator, and in a minute we'll see some more examples where these two operators are not just similar, they're exactly the same. Okay, so so these are the next. These are the basic properties, and for the next two properties, we need the following assumptions. Property, assumption 1: every unit cotangent vector induces an orthogonal transformation of Sx, and property 2. The Clifford multiplication, the Clifford multiplication should be, hold on, what happened? No, this is not supposed to happen. Did I just erase everything? Oh, okay. Well, that was close. Okay, I need to be careful. Okay, the Clifford multiplication, CL TF to star of X tensor S to S needs to be parallel. Then the Dirac operator is self-adjoint. So the index of the Dirac operator is not very interesting in itself, but as we will see, there is often a way to split the bundle S into even and odd parts, and the index of the individual the even to odd component, and equivalently minus the index of the odd to even component will be interesting, and will have a topological meaning. Okay, now I suggest we have a short break, and no PDF. Are there any questions? Okay.
Кстати, вы же экзамен еще не отправляли?
Да. Значит, с экзаменом экзамен я пока не отправлял. Я значит, прошу прощения, попробую сегодня вечером, значит, все отправить. Значит, идея в том, чтобы задачи были, с одной стороны, решаемые, с другой стороны, интересные. И, в общем, пока, к сожалению, пока я этого не сделал, но естественно, сделаю.
Хорошо.
Сколько будет задача ориентировочная?
Ну, ориентировочно 5.
Понятно.
Are there any more questions? Okay, сейчас we have a break, and then after the break, let's see a few examples of the Dirac operator, and well, in particular, are there any people who are interested in the example which was basically the reason Dirac invented the Dirac operator. This example is well, it's not very interesting for us, but it was interesting. It was interesting for Dirac. It's not interesting for us because the manifold in this case will be just the Euclidean space. But still, so this manifold is not exactly what we're after. We want to compute the index of an operator to find a compact manifold. But anyway, well, we could take a look at a few examples with x equal Rn, and then we'll see some more examples. Значит, да, я, значит, в качестве такой опции предлагаю, значит, рассмотреть пример, там, с которого начал сам Дирак. Значит, по счетному примеру многообразие у нас будет просто евклидовым пространством. Нам это не очень интересно с точки зрения вычисления индекса, потому что евклидов пространство не компактно, но, значит, в общем, если есть желание, то давайте рассмотрим этот пример, а потом другие. Okay, so that's I think I saved everything. Okay, let's have a break in 20 minutes. Over the week today. Okay, let's have a break, and then and then we'll probably need to start a new session. So I'll stop recording.